Hi, everybody. Welcome back. It's Tuesday morning, and you guys had a big day yesterday, lots of content, and you started the Harry Potter challenges as well. So, hopefully, you're enjoying that. Today's lesson's not too bad, definitely shorter than yesterday. We have some loose ends to tie up from our last class, a couple slides that I skipped just because that lesson was already too long. So, we're going to go back and fill those in really quick. So, you have this slide in your notes if you printed off my notes. It's also from your textbook. This is a sort of description, a theoretical description of acids and bases in neutral substances, and it was put forth by a Swedish chemist named Svante Arrhenius, and it's the one we use for Chem 30 when we talk about acids and bases. So what is it all about? Well, it's actually pretty straightforward. I'm just going to grab my notes as well. Okay, so Arrhenius's theory says that acids are compounds of hydrogen. Boy, that's messy. Excuse me. Compounds of hydrogen that ionize in water to form H+. So we kind of went through this yesterday. Okay, so not every hydrogen compound ionizes in water, but those that do, we call them acids. So any compound of hydrogen that when placed in water ionizes to form hydrogen ions. And then the second thing that he said is when you have hydrogen ions, they can react with hydroxide ions to make water. And we call that neutralization. Acid plus base makes water, neutral. So that's the Svante Arrhenius theory for acids. Bases are similar. According to Arrhenius, a base is an ionic. So an ionic compound that contains a hydroxide. So ionic hydroxides, and these dissociate in water. So a different term, they dissociate in water to form OH minus or hydroxide ions. So that's where the base part comes from. And I'm just going to grab, I don't have a nice blue here. So now let's see if I can get blue on my palette. There we go. Blue for base and red. Oh, darn it. Red for acid. Okay, so if you're using pH tests, the hydrogen ion turns pH paper red and the hydroxide ion turns pH paper blue on our diagnostic tests. And then the last one, neutral substances. So no H plus or OH minus formed. So any substance that does not form hydrogen ions or hydroxide ions is considered neutral. And these can be ionic or molecular compounds. Okay, so that's sort of the overview of our Chem 20 theory, or Arrhenius theory on describing acids, bases, and neutral compounds. Sorry, that's messy. If you have a hard time reading it, you can find it in your textbook on page 199. I've shortened it just a little bit. Okay, so now that we have this, we can go back and finish off that last chart that we also skipped yesterday. And it was using diagnostic testing, and it's this guy here. Okay, so we have to figure out which of these 7 compounds is KCl, which one's BaOH2 or barium hydroxide, zinc. This one is benzoic acid, calcium phosphate, wax, and that one is sucrose, which you are supposed to remember from chapter 2. Okay, so 7 chemicals, 7 different sets of diagnostic tests. So let's eliminate some right away, some pretty unique ones. So this is the only one that turns litmus paper red to blue. So red to blue means base. So which of those 7 compounds is a base? Well, according to Arrhenius's theory, a base is an ionic hydroxide. So there it is, BaOH2. It's the only one that has it's an ionic hydroxide that can produce OH minus, causing litmus to turn blue. Okay. The other one that's different here is blue turns to red. So that's going to be our acid. So scanning through these, which of these contains a hydrogen that can ionize in water? So that takes a little bit of skill, and if you are really good, you'll recognize it right here. COOH is an organic acid or a carboxylic acid. So this one is called benzoic acid. You don't need to know that, but you should recognize the COOH. So there's our acid, C6H5, COOH, aqueous. Okay, so I'm just going to strike these 2 out. So we've eliminated 2 of them. 5 left. Okay, so high solubility in water. We got 3 of them. So let's see what's going on. Oh, one of them's already done. So 4 is being eliminated. 7 is being eliminated. Okay. So we have 2 left that are highly soluble. One of them does not conduct and the other does conduct. So high solubility. So for these 2, we would use the solubility chart to figure out which ones have high solubility. So when you look them up, you would discover that, let's switch to orange for these. KCl has high solubility and sucrose is polar. So it also has high solubility. So how do we distinguish these 2 to match them up on the chart? Okay, so one of them is highly conductive and the other is not. Which of those 2 would be highly conductive in solution? And that would be your ionic compound, KCl. When dissolved in water, ionic compounds have high conductivity, so that's your key. And molecular compounds like sugar do not conduct, so there's our sugar, C12H22O11. So we can strike those ones out. Okay, so what have we got left here? Let's take a look at this chart. Gone, gone. So we have 3, 5, and 6. Now the tricky thing about 3, 5, and 6 is they are all the same. They have the exact same results. In other words, we can't really eliminate or narrow down any 3. We can just say that 3, 5, and 6 must be calcium phosphate, wax, and zinc. There's no way to distinguish those other than if we had appearance, and we would know that this one is a metal and this is wax, so you would know that it looks like wax, soft, white solid, and then this would be our ionic crystal. So we don't have that information, so we're done. Okay, that's tying up from yesterday. Now we're going to jump into today's lesson. So in your notes, we are looking for the page titled Writing Chemical Reaction Equations in Water. By the way, I posted the answer keys online for this. Hopefully you checked that one and are good to go. Okay, blow past those. Here we go. Chemical reactions in water. So in your notes, you have a couple things to fill in. We assume that for all reactions in Chem 20, they're spontaneous. That means they just happen when you mix reactant A with reactant B. It goes forward and it happens fast and it's complete. By complete, we say 100% of it reacts and it's a balanced equation. So let's say that it looked like that. We'd put a 2 in front. So they happen on their own spontaneously. They happen very quickly. They happen 100% complete, and they always have a balanced chemical equation so that the moles of chemical are balanced on each side. So those are our 4 assumptions. All right, net ionic equations. What are these all about? So single and double replacement reactions often have something called a spectator ion. Now, you know, if you've ever been to a sports game, spectators sit on the side and they watch. They don't take part in the game. So if they're not taking part in the game or the reaction, then they should not be included in the equation, and that's called a net ionic equation. what does this mean? What does this look like? Okay, so I'll show you a couple examples and then I'll just explain the rules. Determine the net ionic equation for the reaction of copper metal with silver nitrate solution. Okay, so before we do a net ionic, we need a balanced chemical equation. Copper solid is copper metal, reacts with silver nitrate. Silver is an Ag plus, nitrate is an NO3 minus, 1 to 1. It's aqueous, I know that because I could look up its solubility. Here's nitrate, and silver's not in the bottom, which means Ag plus is here. Very soluble, so I write it as aqueous. And this is the one I want, so let's get rid of that. Leave it. Okay. So, aqueous. And my products, it's going to be single replacement, so the copper will join the nitrate. CuNO3, which copper? There's two of them, copper 1 or copper 2. So I go look on my periodic table and I discover copper 2 is the most common. So that means copper 2 needs two NO3 1 minuses to go with the 2 plus to balance that formula. And I'll look at the state in a minute. And silver's kicked off and left on its own as silver solid. So that's a single replacement reaction. Okay, state on this one. It's an ionic compound, so we got to go look it up. Nitrate is here. Copper is not there. That means copper 2 plus is in the most. Okay, so that means aqueous. Aqueous. Yuck, what a mess. Okay, so I've got all my states. Is it balanced? No. 2 nitrates, 2 nitrates, 2 silver, 2 silver. Okay, there's my balanced my balanced chemical equation. Everything's good, states are good. Okay, now, are there any spectator ions in here? Anything that's not actually reacting? Here's how you figure it out. So for a net ionic equation, you rewrite it underneath. Anything that is aqueous or highly soluble breaks apart. It dissociates into its ions. So this is made up of 2 Ag plus ions, 2 NO3 minus ions. This one's also highly soluble, so it breaks apart into a copper 2 plus ion, 2 NO3 minus ions, and 2 silver solids. Okay, so now we figure out spectator ions. Is there anything that is not changing on both sides of the equation? In other words, the reactant and the product have the exact same everything, same state, same formula, same symbol, same number of moles. Take a look. Copper solid turns into copper 2 plus, so that's changing. 2 Ag plus turn into 2 Ag solid, so that's changing. 2 nitrate, 2 NO3 minus aqueous is 2 NO3 minus aqueous. Those are the same. They're spectator ions. We cancel them out. They're not part of the reaction. So knowing that, now I can rewrite my net equation with everything that's left. So in this reaction, what's really happening is copper solid is reacting with 2 Ag plus to make copper 2 plus and 2 Ag solid. That is the net ionic equation. So that's the basic pattern to doing these. It'll make sense and sit better with you if we do another example, and then I'll just go through the rules with you. Okay, so second one. Write the net ionic equation for the reaction between solutions. So that means in water, lead 2 nitrate with potassium iodide. Lead 2 plus, nitrate NO3 1 minus. So I'll need 2 of those. And just to confirm solubility on the lead nitrate, so there's my nitrate. Lead is not here, so Pb2 plus is up here in the most. Okay, so that one's aqueous, reacting with Potassium iodide, K plus, I minus, whoops, one of each. And I look up solubility on that one as well. Here's my I minus, K plus is not there, so it's in the most. Okay. Whoops, K plus, aqueous. Becomes, so this is a double replacement. Metals change places, so we get PBI. PB is a 2 plus, I is a 1 minus, so PBI2. Solubility, iodide is here, and PB is down there, so it's a solid. And, yuck, I'm running out of room. PB with the I, K with the NO3. KNO3, plus 1, minus 1, solubility, NO3 minus, K plus is not there, it's up here, so highly soluble aqueous. Okay, balanced. 1 lead, 1 lead, 2 nitrate, 2 nitrate, 2K, 2K, 2I, 2I. Okay, that's balanced. Now, here comes the work. We need to break everything apart that is aqueous. PB2 plus, aqueous. 2NO3 minus, aqueous. 2K plus, aqueous. 2I minus, aqueous. This one's a solid, so it stays together. PBI2, solid. Does not dissociate, it has low solubility. And 2K plus, aqueous, high solubility. And 2NO3 minus, aqueous. I should sneak my plus signs in there. Okay, now the fun part. If you can call it fun, you get to cancel anything out that is a spectator ion. So let's see. PB2 plus goes to a solid, so that's different because here it's aqueous and here it's solid, so we cannot cancel those out. 2NO3 minus aqueous, 2NO3 minus aqueous, gone. Spectator ions. 2K plus aqueous, 2K plus aqueous, gone. 2I minus aqueous, I2 solid, stays. PB2 plus aqueous, 2I minus aqueous, becomes PBI2 solid. So there were a lot of spectator ions in that reaction. This is what's really happening, and we would say the nitrates and the K plus are just on the sidelines. Spectator ions. All right, that's net ionic equations. Now there are some rules, and I've been using all the rules. So let's just take a look at them. Write a complete balanced chemical equation. Whoa. Dissociate all high soluble ionic compounds, which we did. Ionize all strong acids, only strong acids, they would go into their H plus, and whatever's left over as a minus. We didn't have any of those examples. Cancel out identical entities. So those are your spectator ions that are the same on both sides, and then write the new net ionic equation. It says here, in order to cancel out spectator ions, they must be identical in every way. So chemical amount, so 2K plus, 2K plus. So the 2's have to be the same to cancel them both out. If they're ions, they have to both be plus. States of matter, if one is aqueous and the other is solid, you can't cancel them out. They need to have the same state of matter. So those are important little details. Okay, so to finish off the lesson today, we're going to go through 2 examples, and I'm going to have you try it on your own first. And then so you can pause the video, try this one on your own, and then come back and see how you did. Okay? Okay, zinc metal is a solid, reacts with copper 2, so that's 2 plus. SO4 is a 2 minus. It's a solution, aqueous. Looks like it'll be a single replacement. The metals will trade spots. So zinc is also a 2 plus, so we get zinc sulfate. Just check the solubility on that. Sulfate and zinc is not there, so it's in the most category. So aqueous. And copper is left over on its own, so it is the metal that is replaced. Okay. Zinc solid. Dissociate all aqueous high solubility ionics. And last one, copper solid. Okay, get out my canceling pen. What is identical on both sides? Just the sulfate looks like. Gonzo, gonzo, everything else stays. So our net ionic is zinc solid, reacts with copper 2 plus to make zinc 2 plus aqueous and copper solid. Oh, messy, messy. Okay, that's our net ionic equation. One more to practice, then we're done for the day. So in your notes, if you didn't print off the notes, just write it out and try it on your own. Okay, here's the last one to do. So you can pause the video here, try it, and then come back and see how you did. Solutions. So aqueous, barium is a 2 plus, chloride is a 1 minus, BaCl2. I'll just verify that. Chloride right there, and barium is not in this list, so barium 2 plus is up there in the most. Okay, so aqueous, high solubility. Sodium sulfate, sodium is a 1 plus, SO4 is a 2 minus, so I'll need 2 of those. Na plus, SO4 2 minus is right here, and Na plus is here. High solubility. You can see how we're using solubilities on every single one of these. Okay, double replacement, metals trade places. Barium goes with the sulfate. 2 plus, 2 minus, it's balanced. Solubility, sulfate is here, and barium is not in this list, so it's up here. Ba2 plus. Sodium chloride. NaCl. Aqueous. I just want to go back and check barium sulfate again. I think I got that one wrong. I missed it. It's right here. Ba2 plus. My mistake. So this one is actually solid, low solubility. And the NaCl is high solubility aqueous. Okay. Write them all out, break them apart if they are soluble. Ba2 plus. Do you know how many times I write aqueous in a year? The answer starts with 2. Too many. Holy smokes, that was so funny. 2 Na plus. Whoops. SO4 2 minus. Okay, I've dissociated everything that's high solubility and done it really messy. That one's just terrible. I gotta fix that one up. Computer's running really slow here. I'm not sure what's up. Good thing we're almost at the end of the lesson. BaSO4 solid stays together. Oh, I didn't balance this thing. Darn it. Just see that now that I have 2Na here, 2Na there. That's all I had to do to balance it. That's good. Everything else is all right. 2Na plus and 2Cl minus. Both aqueous, highly soluble. Get out my canceling pen. Okay, barium 2 plus is different. 2Cl minus, 2Cl minus, they're gone. Same. 2Na plus aqueous, they're gone. And sulfate is different because here it's a solid. Okay, that's it. Wow, a lot of spectators in there. Barium 2 plus reacts with SO4 2 minus to give BaSO4 solid. Kaboom. Done. Okay, hopefully that seems pretty straightforward to you and you've got it dialed in. Practice. There's one page in your study guide, page 202 for Johnson, 206 for Kelly, which has great questions to do. And I will post the answer key on this lesson so you can practice and check to see that you're getting them right. Okay, good luck, everybody. And hope you're enjoying the Harry Potter challenges. And we'll see you tomorrow.